You may have noticed that in almost all of the polynomial functions that we've considered up to this point, the polynomial expression for the function has been factorable. Now that won't always be the case. So we need some techniques for factorization that we haven't examined before, and those techniques involve polynomial division. Let me backtrack here and tell you why that's the case. Suppose we consider this function, and suppose we know, for no apparent reason, that x equals 2 is a 0. Now, if we know that x equals 2 is a 0, we know automatically that x minus 2 is a factor of this. So if we know that 2 is a 0, x minus 2 is a factor, it means that we could rewrite that function as x minus 2 times some other leftover factor. Now, to identify that leftover factor, it's kind of like this. It's kind of like if I have 24 and I know that 6 is a factor, then I know that 6 goes into 24 evenly, and I know that in making this division possible, I've got, let's see, 6 times 4, 4 times 6, oh, that's 24, and it goes evenly, so I know that 4 times 6 is 24. It allows me then to factor 24 into 6 times 4. So this is how that division idea sort of comes into play, and how it helps us with the factoring. Okay, let's take this problem and actually take the x minus 2 and divide x minus 2 into that. Now, I'm showing the division over here as a long division problem, and indeed it is. And we go through it in exactly the same way that we go through division in arithmetic. That is, we're thinking x minus 2 into all of this polynomial. Okay, I want x minus 2 into just the first two terms, but really I can consider just x into this term. So I go, x goes into 6x cubed how many times? Well, I can come out over here and I can write 6x cubed over x and see the cancellation and see how many times it goes. Or I can just imagine what times x is 6x cubed. Well, it would be 6x squared times x to give 6x cubed. Now, notice where I'm going to put the 6x squared. I'm putting it above a term of the same degree. So I want to line up terms of the same degree here in columns. All right, 6x squared times x is 6x cubed. And then 6x squared times minus 2 is minus 12x squared. Now our prescription for long division would be to draw a line and subtract. That is, we want to subtract this polynomial from that polynomial. But you notice we have a minus sign preceding a parenthesis here, so we would need to change the signs here and then collect. Well, to accomplish that sign change, rather than looking at it like this, I'd rather consider it like this. This is a lot safer. I know and can anticipate that I'm going to change those signs, so I'll do it like this. I'll say, okay, this is an understood plus sign, I'm going to make it a minus sign. And this is a minus sign, I want to make it a plus sign. Now notice how I put a circle around the existing sign here, and then I change the sign, I put the changed sign above that circle. Now that's only to emphasize the idea that the sign change has been accomplished, so that if we go through this problem and we want to check to see if we've gotten it right or check the procedure in it, we can always look at these sign change situations to verify that we have made the sign change. Okay, now I can emphasize it here too by saying, okay, this was plus and now it's minus. Now this one is not so terribly important though, because we're always going to set up these two terms to look identical so that when we subtract this from that, it's going to go out. It's going to be a trivial collection. Here's where all the action is. All right, I'm collecting negative 19x squared with plus 12x squared. That's negative 7x squared. Now, so we've identified the item up here, multiplied, we've subtracted, we get this as the result. This is the difference of those two. And now our prescription in long division would be to bring down the next term and start the process again. So we bring down plus 16x, and away we go. We say x minus 2 goes into this binomial how many times? Well, we think x goes into this first term how many times? X goes into minus 7x squared minus 7x times. So we put minus 7x here, and we multiply around like we did before. Minus 7x times x is minus 7x squared. Minus 7x times minus 2 is plus 14x. Draw the line and subtract. That means change signs and collect. Change signs, change sign, and collect. Now this is trivial. Again, I wrote the sign change just for emphasis here, but really we can actually leave this off because we're setting this up so that these will collect to be 0. We set it up that way by the nature of our technique. Okay, 16x minus 14x, that's 2x. Bring down the next term and start the process again. X goes into 2x 2 times. 2 times x, 2x. And then 2 times minus 2 is minus 4. Draw the line and subtract. Well, subtract means change the sign and add. Minus 4 plus 4, that's 0. The division went evenly. Well, we expected it to go evenly. We knew that x minus 2, because 2 is a solution, x minus 2 must be a factor, and if it is, then the division here has to go evenly. But what this tells us is that it's kind of like the 6 into 24 goes 4, 4 times 6 is 24 idea. Well, this polynomial times that one will give this one. And so we have a factored form of this polynomial, and these are the two factors. So let's come back over here and write that factored form. You see, we can actually identify then this other polynomial factor as 6x squared minus 7x plus 2. Now we can continue with the full factorization of this polynomial, just for emphasis here. We're not going to construct this graph or anything, but here's what we would try to do in this process a lot of times. We go through this long division to identify factors, and then once we get to a quadratic polynomial factor, you see, then we can factor by using our regular methods. And I think, let's see, for 6x squared, it's 3x times 2x. And the last sign is positive, so these signs are the same. Middle sign is negative, so it's minus, minus. The factors of 2 are just 2 times 1. The 2 can't go here because it would create a common factor situation, so the 2 must go here and the 1 here for the factored form. Notice that the request for division can be made in a couple of different ways. We have the request as a fraction here and the request as a long division problem. So either way, they're just equivalent to one another. Notice that in writing the long division algorithm or problem that we have 0x cubed, and that's because we're missing an x cubed term up here in this numerator. All right, so here's our divisor, our dividend. We're looking for the quotient. And away we go with our long division. X into x to the fourth goes x cubed times. So we write x cubed here under the term of the same degree. X cubed times x is x to the fourth. X cubed times 3 is 3x cubed. Draw the line and subtract. Change the sign and collect. 0x cubed minus 3x cubed is minus 3x cubed. Bring down the next term, and away we go with the division again. We have x into minus 3x cubed is minus 3x squared. So minus 3x squared. And then multiplying back, minus 3x squared times x minus 3x cubed. Then minus 3x squared times 3 is minus 9x squared. Draw the line and subtract, which means change the sign and collect. Minus 10x squared plus 9x squared is minus 1x squared, or simply minus x squared. Bring down the next term, that's minus 2x. And then x into minus x squared is minus x. Minus x times x is minus x squared. Minus x times 3 is minus 3x. Draw the line and subtract. Change the sign and collect. Minus 2x plus 3x is x. Bring down the next term, 4, and start again. X goes into x one time. 1 times x is x, and then 1 times 3 is 3. Draw the line and subtract, change the sign, collect. 4 minus 3 is 1. Now notice the remainder this time is 1. The division didn't go evenly. Now what are we going to do with that 1? Well, sometimes we're required to show that as a remainder in a particular algebraic form. Sometimes we just say remainder is 1. But remember what we do when we are talking about long division and the division doesn't go in arithmetic. If we have something like 5 into 11, then it goes 2 times. 2 times 5 is 10. The remainder is 1. What do? We put the remainder over the divisor, you see. And we actually write this as 2 1/5. It's really 2 plus 1/5, though. We write it as 2 1/5 like this. But we're going to think about it like this for our polynomial type of division. Our complete answer would be all of this polynomial plus the fraction, let's see, remainder 1 over divisor x plus 3. So that is then our complete answer. Now, you may have noticed that in this long division process, we're using the two most difficult operations. Out of the 4 fundamental operations, adding, subtracting, multiplying, and dividing, the 2 difficult ones are subtraction and division. Now, what if we could invent a technique which would allow us to trade in subtraction and division for adding and multiplication? Well, we can actually do that here, and it's called synthetic division, and I want to show you the process using this same problem. Because we know how difficult this was, I want to show you how easy the synthetic division is. Okay, let's get rid of all of this. Now, here's what we do. And I'm going to tell you the limitations on synthetic division in just a little bit, but right now, here's what we do. All right, we're dividing by x plus 3. Synthetically, we would divide by -3. Now notice that the sign change occurs here. And the sign change is occurring for that trade-in of the more difficult operations for easier operations. Now I'm going to set up the situation like this. No division symbol exactly. It's just kind of a notation that we use for this purpose. All right, I'm going to write in this row the coefficients and the constant for the polynomial that we're dividing into. Now, I'm just going to use a 1 here. I'm going to ignore the x to the 4th business. You see, we don't really use those variables and their exponents in this process except for lining up purposes, and that's about it. So they're not really active participants in the division process anyway, so we really don't need them. All right, then 0, and then -10, and then -2, and then 4. Okay, so coefficients and constant involved in this polynomial. Now, here's how the process works. Take this first entry and just bring it down. And then multiply -3 times 1 to get -3. And then add these two to get -3. And then multiply these two. You see, -3 times -3 is 9. And then add those two to get -1. And then multiply. You see, what we're doing here is we're multiplying, adding, multiplying, adding, multiplying, adding, rather than divide, subtract, divide, subtract, divide, subtract. So we're using the easier operations of multiplication and addition, and we can go through this process very quickly. All right, we're at this point, we're multiplying here. -3 times -1 is 3. Add these two. See, -2 with 3, oh, that's 1. -3 times 1 is -3, and then adding these two, we get a 1. Now, the entries down here turn out to be coefficients and the constant and the remainder involved in our answer polynomial. This is the remainder. The last entry is always the remainder. And these are the coefficients, and that's the constant involved in the answer polynomial. Now, all we have to do to identify the polynomial is say, okay, we divide it into an entry here associated with an x to the 4th power. This entry in our answer is going to be just 1 degree less than that. So this is 1x cubed. This is -3x squared. You see, just kind of follow your nose down. Just go with the decreasing degree of each in each term. This is -1x, and this is +1. And the remainder is 1, so it's remainder over divisor. Now remember, the divisor is that polynomial divisor that we started with. It's the x plus 3 business. And what we have here is precisely what we have right here. So synthetic division is a way to really streamline this situation. Now, let me caution you, though, about synthetic division just a little bit. It has some limitations. That is, it only works in certain circumstances. And those circumstances are, number one, our divisor here has to be a binomial. And not only that, it has to be a first degree binomial. That is, the exponent here is only a 1. And the coefficient has to be 1. Now that seems to be a rather severe kind of restriction on our divisor. But it turns out that synthetic division is an extremely powerful tool, as we'll see shortly. Let's run through another division problem using synthetic division. Here we're taking this polynomial and dividing by x minus 6. Now, to divide by x minus 6, synthetically, we put 6 in this position, and then along this row, we enter the coefficients and the constant involved in this polynomial. So we'll have 3, and then leave some space, then minus 16. And notice there's no first degree term in this polynomial, so we need a 0 for a placeholder for that term, and then minus 72. All right, and then we go through the synthetic division process. We bring down the 3, and then multiply, add, multiply, add, multiply, add. 6 times 3, 18. Adding here, negative 16 with 18, that's 2. 6 times 2, 12. And then adding, 12. 6 times 12, 72. Adding, collecting, you see, we get 0. So 0 then is our remainder. That means the division went evenly. Now our answer polynomial is right here, but the fact that our division went evenly implies that we can show a factored form. That is, x minus 6 went into this rascal evenly, and so we can factor that as x minus 6 times whatever our answer was. To emphasize that, it's this idea, that 3x cubed minus 16x squared minus 72 can be rewritten as, let's see, our divisor was x minus 6, and our answer in this synthetic division process was, well, let's see, it's 3x to an exponent 1 smaller than the exponent on the term implied by this entry. Now remember, this came from the 3x cubed. It came from this business. So what we have here is 3x squared, and then plus 2x, and then plus 12 as the factored form. And we may or may not be able to continue the factorization, but the point is that when the synthetic division goes evenly, it implies a factored form. Now, this is cleverly called the factor theorem. But it is then a way to test to see if we have a factor of a polynomial. That is, if we're testing to see if x minus 6 is a factor of this, then we would go through the synthetic division process, and if that remainder is 0, then yes, it is a factor, and if the remainder is not 0, then no, it's not a factor, you see. So we can make a determination about factorability, or whether or not we have a factor by using this process. Here's another problem. Let's say we're just looking to discover the behavior of the graph on this problem, and we're going to begin with a point plotting method. We know by the leading coefficient test that the behavior left and right side of the coordinate plane is going to be different because that's an odd exponent. We know that because this is positive, it's going to rise to the right and drop to the left. All right, we know that much. Now let's think about the behavior kind of in the middle of the coordinate plane. Let's begin by building a table of values. Okay. F of 0, well, let's see, it's pretty easy for us to tell what y is when x is 0. If x is 0, these two terms go out, and y is negative 12. All right, f of 1, that's pretty easy also. 1 cubed, and then negative 13 times 1 is negative 13. 1 minus 13 is negative 12. Minus 12 minus 12, that's minus 24. All right, that's easy enough. Now, for f of 2, we can do this. We would need to find y. Now, it would be f of 2 that we're finding. We could say y equals if we want to, and just replace x with 2 everywhere we see an x. So it would be 2 cubed minus 13 times 2 minus 12. And evaluating, let's see, 2 cubed is 8 minus 26 minus 12. Collecting here, we find f of 2 to be negative 30, and we would put that into our table of values. But there's another way to find f of 2. Now, this is one of the great mysteries of mathematics that I'm about to reveal to you. So prepare to be awestruck and inspired. If we use synthetic division like this, watch this, it's 2 synthetically into our original polynomial, the 1, now let's see, we have no second degree term, so I'm going to use a 0 and then negative 13, negative 12. And now here we go synthetically. Bring down the 1, 2 times 1, 2. Together here, 2, 2 times 2, 4. Together here, negative 13 with 4 is negative 9, 2 times negative 9, negative 18. Together, negative 30. Negative 30 turns out to be f of 2. So f of 2, negative 30. We can actually evaluate functions at certain values for x by using synthetic division. This is cleverly called the remainder theorem. The remainder turns out to be f of the divisor, the synthetic divisor. And so we can build our table of values using that idea. It's more efficient than this notion, especially when the function becomes a little more complicated or when the number we're trying to plug in gets bigger and bigger. Well, let's go through it with 3 and 4. Let's see, if we want f of 3, then we would synthetically divide by 3. And it would look like this. So let's see. F of 3 means 3 into 1, 0, negative 13, negative 12. And bring down the 1. 3 times 1, 3. Together 3. 3 times 3, 9. 9 with negative 13 is minus 4. 3 times minus 4, minus 12. Together minus 24. So f of 3 is negative 24. So the point 3, negative 24 is on the graph. Then f of 4 is found by, let's see, 1, 0, negative 13, negative 12. Bring down the 1. 4 times 1, 4. Together 4. 4 times 4 is 16. 16 minus 13, 3. 4 times 3, 12. 0. Oh, happy day. We have a 0 of our function at 4. So 4 goes to 0. Let's plot these points. We've got, let's see, 0 goes to negative 12. Gee, all of these appear to be off the graph. But what I'll do is this. I'll just manufacture some points down here just for reference. 0 goes to negative 12. It's down here somewhere. 1 goes to negative 24. It's a lot further down, but I'll just put a dot right here. 2 goes to negative 30. That's even farther down. That's way down here. And then 3 goes to negative 24. We're back up to this point, you see. And then 4 goes to 0. Well, 4 goes to 0. And this graph then is kind of blasting off in this direction. So it goes way down here and then it's sort of coming back up. The graph looks like this so far. All right, now we'd like to know some things about the behavior of the graph to the left of the origin. So we'd like information about f of negative 1 and maybe negative 2 and maybe negative 3. And we can use this same technique of synthetic division. But you know what? Since we got a 0 of our function at 4, if 4 is a 0, then x minus 4 is a factor. And so we can write a factored form here if we want to. Let me just erase this top part here, and I can then write f of x in a, at least partially, factored form. I can write f of x as, let's see, 4 is a 0, so x minus 4 is a factor, and the other factor is found as the answer in this synthetic division process. This is 1x to an exponent 1 smaller than that, which is 1 smaller than this, so it's simply x squared. And then plus 4x, and then plus 3. And then I would look to factor this quadratic factor, and it does turn out to be factorable as, let's see, x times x for x squared, all signs are plus, factors of 3, the 3-1 combination. Oh, great, we've identified a couple more zeros here. When x is negative 3, this factor is 0. So x equals negative 3 is a 0, x equals negative 1 is also a 0. So negative 1 goes to 0, negative 3 goes to 0, and our graph is really starting to take shape here. We don't know much about negative 2 yet, but over on the graph now what we might do is just plot, let's see, negative 1 is a 0, and negative 3 is a 0. So presumably that graph is going up. It's going through this point. It goes up here somewhere. We'll identify it in a second. Comes back down and goes through this point and exits south here in a rather big way, I would imagine. We have our 3 x-intercepts, and that's all the intercepts that are possible here. All right, let's find f of the negative 2. And I'll just put in the negative 2 here and erase all this business. And away we go. The remainder is going to be positive, I'm thinking, because of the nature of the graph over there. But let's see. Bring down the 1. Negative 2 times 1 is negative 2. Together we get negative 2. Negative 2 times negative 2, 4. Together, negative 9. Negative 2 times negative 9, 18. 18 with negative 12 is 6. So f of negative 2 is 6. So the point negative 2, 6 is on the graph. Negative 2 goes up to 1, 2, 3, 4, 5, 6. And our graph looks something like this. Now that 6, that spot, is not necessarily a relative maximum, but we're treating it as such for this problem. And our graph looks like this. In our investigation of polynomial functions, we make some observations and some calculations. We made observations like the leading coefficient test, and we make some calculations like our synthetic division to identify zeros and factors and whatnot. Well, we're going to go through a couple more observations and calculations here in an effort to be able to handle more and more complicated polynomial functions. The next technique we'll talk about is called the rational zero test, and it works like this. Suppose we have a function like this. It turns out that just by observing and making a little calculation on the leading coefficient and the constant, we can determine all of the possible rational zeros. Now, here's how the calculation is made, and I'll show you how it's used in just a minute. But all of the possible rational zeros can be calculated by writing all of the fractions possible using the factors of the constant in the numerator of this fraction and the factors of the leading coefficient as denominators of the fraction. So we have, let's see, factors of the constant. The constant is 10. So all the factors of the constant would be plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. And now in the denominator, we have factors of the leading coefficient. The leading coefficient was 5, so all of the possible factors, plus or minus 1, plus or minus 5. Now, we have a little list to go through here. We have all of these guys over 1, and then all of these guys over 5. That's the complete list. Well, we put all of these over 1, and we just have all of these items. So we have plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. Then we go through all of these over 5. Well, let's see. Plus or minus 1 over 5, plus or minus 2 over 5, and then plus or minus 5 over 5 is just 1. We already have it in there. Plus or minus 10 over 5 is plus or minus 2, and we already have it in there. Now we have this list of all of the possible rational zeros. And you might be thinking, well, why do we want to go through all of this trouble to identify possible rational zeros? Well, this is a test. This is a technique that you would use when you sort of bump into a need for it. And here's how you might bump into that need. Let's say that we begin with this problem to build a table of values. Now, here's our function, and let's build a little simple table of values just right up here. We're going to just start with an x and y, xy pairs, and let's just say x is 0. Now, if x is 0, all of these terms go out, and we have 10. So when x is 0, y is 10. Now, what about when x is 1? If x is 1, then we have 5 minus 2 minus 25 plus 10. Let's see, 5 minus 2 is 3. 3 minus 25 is negative 22 plus 10 is negative 12. So when x is 1, y is negative 12. Let's put these points onto a coordinate plane. Now, just relatively speaking, 0 goes to 10 is just up here somewhere. And 1, negative 12, is down here somewhere. Now, with the intermediate value theorem, we know that there is a crossing in the interval from 0 to 1. So we have a 0 in here. And you know, zeros, if we can identify a 0, it can lead us to a factor, and that will kind of make the function a little more, a little easier to deal with. All right, so we are hoping that that crossing is rational. Now, to test whether or not we have a rational value for the 0 of the function, we can use the rational zero test to determine which items we test for. You see, there are an infinite number of rational values between 0 and 1. Which ones do we test for? Well, we use our rational zero test, and we realize that between 0 and 1, the values in that list that are possible would be simply 1/5 and 2/5. So that's all we need to try. All right, so let's go through and try those. We would have, synthetically now, we would divide by 1/5. And so bring down the 5. 1/5 times 5 is 1. -2 with 1 is -1. 1/5 times -1 is -1/5. Uh-oh. Together we get -25 and a fifth. Uh-oh. 1/5 times -25 and a fifth is a mess. And when you add 10 to this business, you certainly don't get -10 here, you see, to collect to get 0. So this value is not 0. That's the point here. All right, so 1/5 is not a 0 of the function. Now let's try 2/5. Bring down the 5. 2/5 times 5 is 2. 2 with -2 is 0. That's nice. 2/5 times 0 is 0. Together, -25. 2/5 times -25, the 5 and the -25 cancel, leaving -5. 2 times -5, -10. 10 with -10, 0. So we do indeed have a 0 at 2/5. Now, not only does that tell us that at 2/5 we have a crossing, and therefore we can kind of draw this part of our graph, and we don't know how it behaves after this, but when we can make some discoveries about that. The important thing here is that with this 0, we can go through and factor our function. Now, our function was a third-degree polynomial function, and when we snag out this factor, a linear factor that is composed of this 2/5, then we'll have the other factor will be a quadratic function. Now, the other factor is just right here. It's 5x squared minus 25. All right, so we can go through the factorization like this. All right, so our original function was this, and now with 2/5 as a 0, x minus 2/5 is a factor, and the other factor we read from the bottom of the synthetic division, and here it is. And now away we go with continuing to factor and identify zeros. I see a common factor here of 5, and I'll take that out. And now I'm looking to factor this. Gee, it's not the difference of squares. So I have to kind of solve it another way. I have to think this way. I have to think, well, what values of x will make x squared minus 5 equal to 0? Adding 5 on both sides, x squared is 5. By the square root property, x then is plus or minus the square root of 5. Aha, here are the other two zeros. So now I can continue the factorization. If these are zeros, they lead to factors, and so I can write those factors. On the way, though, I'd like to show you this, that a lot of times when a linear factor contains a fraction like this, you'll get a common factor in other parts of the function, like here. And it'll turn out a lot of times that that common factor can be multiplied through this binomial factor in order to clear the fraction. Here's what I mean. In this next step, if I multiply 5 times these two, I get 5x minus 2, you see. So I have a linear factor that has rational numbers. Well, actually it has integers as coefficients. And now this factors to, well, let's see, it's x minus each of these. So x minus the square root of 5 and x minus the negative of square root of 5, or x plus the square root of 5. So here then are our 3 linear factors and our 3 zeros. Well, let's make sure we understand what they are. Here are 2 of them, and the other one was found earlier as 2/5. So x equals 2/5 is that third zero. All right, so we have zeros and the same number of linear factors as we expected. Here's another situation where the rational zero test might come in handy. Suppose we begin with this function, and looking at the constant and the leading coefficient, they're both 1. So the possible rational zeros, that list is pretty limited because we have plus or minus 1 over plus or minus 1. So all of the possible fractions that can be made out of this would be plus or minus 1. Now, f of 1 turns out to be, and notice I'm evaluating f of 1 and f of negative 1 kind of by hand because there's no sense in going through the synthetic division process for this purpose. It's just too easy. So f of 1 means replace x with 1 and evaluate. We have 1 cubed plus 1 plus 1, that's 3. F of negative 1 is negative 1 cubed, which is negative 1. And then with negative 1 and 1, we'll give negative 1. Well, how does this help us? Well, it turns out that, gee, if these are all of the possible rational zeros, neither one of them produces a 0 for our function. So how does this really help us? Well, we might notice here that that 3 and negative 1 are on opposite sides of the x-axis. So there's a crossing between these two. That is, if we're thinking graphically here, we think this way. We think, well, f of 1 is 3. F of negative 1 is negative 1. So there's a crossing within the interval. What about f of 0? Let's see what that gives us. Well, up here, if x is 0, these go out and we have 1. So f of 0 is 1. Aha, now we've narrowed our crossing to the interval from negative 1 to 0. Can it possibly be a rational zero that's in this interval? No, because we have tried our rational zero test here. We know that all the possible rational zeros are plus or minus 1, so we know that this zero is irrational. If we want to identify it, of course, we can use our calculator, put the graph onto the calculator and zoom in as many times as we'd like. But what we determine by using the possible rational zero test is that that zero is irrational.